Okay, we're going to start talking about solar and terrestrial radiation. So basically, we'll be talking about radiation. I am not sure how many of you are familiar with it. Uh, so we're going to look a little bit in depth at geomagnetic radiation. Uh, and this is a way for the energy to flow into and out of the Earth atmosphere system, and it maintains us a very stable and habitable planet. So, what is electromagnetic radiation? Well, everything, believe it or not, throws off some kind of electromagnetic radiation. And you listen to it, radio waves. If you listen to the radio, the satellite beams you come back and forth, you hear using satellite radio, whatever, is another method. Uh, all these are electromagnetic radiation. Bluetooth on your cell phones is another form of electromagnetic radiation. It is a wave energy. So, yes, it is shaped like a wave. And here you can see a kind of a general spectrum of it. And notice how much the small area is that we actually can see. There are infrared, there are X rays that some of us get. There are gamma rays that come out of your uranium and all. So, all kind of electromagnetic radiation. Every object that is around us pretty much emits it. So here is a look at what they are. They have a wavelength. Basically, it's the distance between two crests. I go out to the ocean a lot, and if I'm out in the ocean and I'm getting beat up by waves, uh, you'll notice that one hits you, then the water goes down, then another one hits you. The timing and the distance between those hits is the wavelength. And how frequently you're getting hit, like some days you may be getting hit every few seconds or farther apart. That's the frequency of the wave. And since electromagnetic radiation always moves at the speed of light, the shorter the frequency, the more energy that wave has. The longer the frequency, the more slower it is. In essence, there's less energy there. All right, a black body, and we are going to make the assumption that everything pretty much is a black body. It absorbs all the radiation and it emits every piece of energy that it receives. So we're assuming it's a perfect absorber and a perfect emitter. Not reality, but for purposes of meteorology for right now where you're at, it works. So the wavelengths, that is a black body, is inversely proportional to its absolute temperature. So think about the difference in temperature. Earth, what's its temperature? About average, maybe 60 some degrees. If you look at the poles and all, upper 50s. What's the sun's temperature? Way, way, way larger than that. And we just learned that it's proportional to its absolute temperature. Well, guess what? We're saying then that the sun's wavelengths are way shorter than the Earth's. And here you can see that. And that's why the light that we seek is in the we don't see all the intense sun rays, which are more ultraviolet, but we do see the light coming off of the surfaces around us that are more visible light. Also, the amount of energy from a wave is proportional to that same temperature to the fourth power. So basically, you're multiplying something by itself 4 times. So think about it. Sun, a large number, multiplied 4 times. Way larger number. Phenomenally large. Earth, not too bad, but it's a much smaller number. Still multiplying 4 times. That's a pretty decent amount of energy, but nothing compared to the sun. Okay, when you're looking at the sun, though, you get further and further away, you're not getting as much radiation from the sun. So as you go away, you're getting less, and it's basically 1r squared, or the radius away from the sun squared. So if you increase the radius from the sun, say 4 times further than the Earth is, it would be 1/16 the amount of energy, 4 squared. So Another aspect of this, all right, is solar altitude. Many of you are living in Ohio or West Virginia and maybe around the world, even some other spots. All right, so the sun at the equinox at September 21st or March 21st, the sun is right directly over the equator, pointing directly at it. Look at a flashlight. Notice how small that circle is where it's pointing at it. That same amount of light is over a very small area. Now, say you live much further north at that time, well, then that sun is not directly overhead. It is coming at an angle to you, and your light is spread out, like flashlight B has. So you don't have as much energy coming into your area. It's being same amount of energy is coming out of the sun, but it's being spread out over a larger area. That explains why most of the energy from the sun hits around the equator. So here you can see it at the equinox, different latitudes. Basically, it's the latitude you're looking at, except opposite, where pole would be up here, the sun at the equinox is just nicking it, and the sun is nicking the south pole. 45 degrees, you got an angle of 45 degrees. You could literally put a beam of light out there or whatever, flashlight, and see that that angle just spreads out much further at that angle. And here you can actually see the amount of radiation that we receive. Notice, up in the Antarctic area, 90 degrees south, there's nothing. In the wintertime, there, they receive absolutely no solar radiation. Now, down across Singapore, which is near the tropics, it's near the equator, it's just having a slight fluctuation depending on whether the sun moves north or south of it. Just a little bit difference. And there's a much bigger difference if you're, say, in New York or in Ohio, West Virginia, mid-latitudes. There is a lot of difference between the amount of energy you receive in the wintertime and the amount of energy you receive in the summertime. And here you can see how it lines up. The Earth never changes its tilt. However, in relation to the sun, it does appear to change. This is still tilted this way. When it's over here, it's still tilted the same way. But that sun, when you're looking at it, would appear to be northern hemisphere here, southern hemisphere here. So, all this solar radiation that's hitting the Earth, what happens to it? Well, according to the conservation of energy within the atmosphere, it's either got to be absorbed, reflected, or retransmitted. And that is the way that we keep our temperature the same through all of those. And if you look at our average temperature, yes, it's fluctuating and changing and maybe warming slightly, but overall, it's staying fairly doggone constant. So we have really a very good balance. Conservation of energy works very well for describing Earth's energy. Now, what's scattering? Well, ever look up in the blue sky? It's called me scattering. You're not going to get it in here. But that is actually our atmosphere scattering light waves across. And yes, when a light wave strikes a cloud or dust object or even the atmosphere somewhat, you know what? It's going to scatter, and not just in any one direction, but in all directions. So some of that energy is still going to make it to Earth. Some of it's going to go back into space. Some of it's going to move all around. Reflection is another one, or albedo. You ever been outside right after a major snowstorm? You got to wear sunglasses if it's a very bright, sunny day. The reason for that is that snow has a very high albedo, very reflective. Now, the same token, go into the woods. Woods don't have much, very low albedo, so the sun is not being reflected back into space as well. And some of that energy is absorbed in the upper atmosphere, especially in the chain reactions that occur with ozone, which protects us. And you can see the solar radiation in the Earth's surface here. Reflection where the snow cover is shows up very nicely. There's some in the West Virginia mountains here, northern Ohio here, right off the Great Lakes. And then up in Canada, there's a bunch of snow. Notice how dark the ocean appears. Ocean really absorbs energy. And here is what actually constitutes our planetary system. 30% of the solar energy is reflected into space. 23% is absorbed by the atmosphere, and 47% is absorbed by the Earth. And it works out that that gives us the temperature that we maintain. And here you can see that. So there is a radiative equilibrium for the world. Now, greenhouse gases do impact this. So the Earth's surface, because it is not as hot as the sun, has longer radiation. It's called infrared radiation. And these greenhouse gases are transparent to the ultraviolet or visible radiation, but they absorb infrared. Gases such as methane, carbon dioxide, water vapor, all absorb infrared radiation. So guess what? When they absorb it, they either emit it back into the Earth, back into space. So they are what keeps us a little warmer than we would be without them. And here you can see the amounts of different greenhouse gases that are out there. Water vapor is the most. And water vapor is the most important. You're going to be asked that question. Why do you think water vapor is the most important greenhouse gas? Well, compare the desert Southwest and the Gulf Coast. Both at the same latitude, roughly. Both getting the same amount of solar radiation. But as a greenhouse gas, there is a lot more water vapor along the Gulf of Mexico. What that does is, at nighttime, when all the infrared radiation from the Earth is going out, there's no solar radiation coming in, it's getting absorbed by that water vapor and being emitted back down to Earth. Temperature stays significantly warmer at night along the Gulf Coast than it does in the desert Southwest. Southwest at night, you may get down, really drop the temperature from the daytime highs because the air is dry. So there's no. And the calendar effect is just a look at the CO2 levels taken at Mauna Loa, which is very much in the middle of the Pacific Ocean. So it's just looking at CO2, not taking anything else into account. And you'll notice that with CO2, though, there is a variation between summer and winter. So that is because the plant life is more active. So the only thing I wanted to kind of look at otherwise, just to give you an idea how useful understanding radiation is for looking at weather. I'm looking at satellite pictures here. We talked about the visible, which is geocolor. Let's say I wanted to look at other bands. Yes, the Earth emits radiation in different wavelengths. So here is band 1, which is a blue band. Here is band 2, which means more red. Here's one that, another infrared band, just slightly different, 0.86 microns. It looks at more vegetation. Then we can look at 1.37, and guess what? We're getting more up into the cirrus level. Maybe snow and ice we want to see more. Cloud particles, shortwave. And then we get into water vapor. At different elevations, it has a different bandwidth. So you can see there's all these different bandwidths, and we can determine things about the atmosphere from them. Very, very useful to understand this and look at it in terms of satellite. So hope you got something out of all this. Please don't hesitate to ask if you have any questions.